somewhat in balance.
Committee, the ISDC committee. Delighted to have you here on Friday, second day of Congress. And I've been wondering what an audience of folks here to see what nuclear propulsion looks like. And certainly the President. Glad that you're here.
Right.
President. We'd like to conduct the hours to be closed at 5 minutes of the end. And so that if you have time for questions, you can plan on that. Our presenter today is Dr. Stanley Borowski. He's a senior research engineer at NASA Lewis Research Center's Advanced Space Analysis Office located in Cleveland, Ohio. His overall responsibility includes nuclear thermal rocket propulsion systems analysis, vehicle design, and moon, Mars, and mission analysis. His current work on the commercialization and human settlement of the moon is focused on identifying critical technologies, development of viable lunar space industries. Dr. Borowski received his doctorate in nuclear engineering at the University of Michigan. Prior to joining NASA in 1987, he worked at the Propulsion Research Institute in Sacramento, California, in the area of advanced nuclear propulsion, and at Oak Ridge National Laboratory's Fusion Engineering Design Center in Tennessee, in the areas of plasma engineering and fusion reactor design. Dr. Borowski's talk will be nuclear thermal rocket propulsion with a K. Please welcome Dr. Borowski.
First of all, I'd like to say good morning, everybody. I'm pleased as punch that the weather is nice. Last night when I was going to bed, it was all rainy. I said, boy, by the time I get in here at 9 o'clock in the morning, there'll probably be maybe 2 or 3 people, and they'll just be setting up. But I really want to thank you for making the effort here, and I'm glad that the sun is shining. What I'd like to do today is, in the time I have allotted to me, I'd like to discuss a little bit about what a nuclear rocket engine is, about some of the work that was done in this country during the 60s and up to the early 70s, and then tell you about where NASA's been going. A lot of people probably have heard about the Space Exploration Initiative and its subsequent demise. And then what I like to do is tell you about some of the innovative techniques and ways of looking at certain technologies that we've been considering since 1993, and various concepts that we think can potentially enable NASA to allow and others of the nation's space programs to truly open up the space frontier to people, not just a few scientists and astronauts. Open it up for the general public, and economical space transportation, I think, is one of the key ingredients. The second part of that title is the nuclear thermal rocket with a kit, the LOX augmented nuclear thermal rocket. Essentially what I'll be talking about is a conventional nuclear thermal rocket with an oxygen afterburner, and how we marry those two technologies together, and what are some of the capabilities that this system can provide for us. Am I in anybody's way? Are you really shut down? Briefly, what I'd like to go over, I'll give you some introductory and background information briefly on nuclear rockets and the NERVA program for those of you who are unfamiliar with it. Discuss the LOX augmented nuclear thermal rocket concept. Describe how that concept compares with conventional chemical rockets as far as a representative lunar mission. How might we go back to the moon to set up a base, and the procedure and the focus and the emphasis of something like that, and what the benefits are of going without using lunar resources versus using lunar resources. And then also, I think this concept is truly revolutionary. A lot of people say, oh, I got something that's revolutionary, and the word is often overused. It really isn't revolutionary. But I really do think here that the marriage of the two technologies that I'm about to talk to you this morning can lead to some pretty remarkable stuff, like 24-hour one-way trips to the moon, from Earth to the moon in 24 hours, just like in the movie 2001: A Space Odyssey, with technologies that I think that NASA, the country, industry, other national space programs of the world can develop in the next 10 to 15 years. So we're going to get into that, and then I'll come up with some summary and conclusion remarks. For those of you who are unfamiliar with a nuclear rocket engine, it's really kind of a monopropellant version of a chemical engine. I mean, a chemical engine uses liquid oxygen and liquid hydrogen, mixes them, combusts them, the energy and its distribution among the reaction products are exhausted out a nozzle. That imparts momentum to the spacecraft, thrust, and acceleration. The nuclear rocket is kind of a monopropellant version. All we do is rather than using chemical combustion, we use a nuclear reactor core, shown here in red, as our heating source. And we use lightweight monopropellant system, namely liquid hydrogen, as both our coolant and our exhaust propellant. That allows us, since thrust is proportional, and specific impulse is proportional to the square root of the exhaust temperature of the gas coming out over the molecular weight for a given temperature, say 3,000 degrees Kelvin of the exhaust products. If we use a lighter molecular weight fluid, those particles can be heated and exhausted out at higher velocity. So essentially a nuclear thermal rocket can provide twice the specific impulse or twice the fuel efficiency, if you will, of a normal chemical rocket. So rather than carrying 500 tons of propellant for the same amount of mass, a nuclear rocket engine would only need about half that. So we can carry more payload, more productive components and technology and equipment to the moon or Mars, wherever our destination is. So it's a very valuable technology. NASA became interested in this technology shortly after its formation in 1958. And they thought about using NTRs for really difficult space missions. And at that time, they were talking about extended lunar missions, lunar-based construction and operation, and then ultimately missions to Mars and beyond. And a joint, at that time, Atomic Energy Commission at NASA, they created the Space Nuclear Propulsion Office and initiated essentially the beginning of the rovers and the NERVA program. And what a lot of people don't, probably are unfamiliar with, and I'll show this question out as a general one and see how many hands I can get. Everybody is familiar with President Kennedy's moon speech, right? I mean, 61, I want to send men to the moon and return them safely before the decade is out. Does anybody know what that was just one of 4 items that he mentioned in that same speech, but we never get past the first one. Does anybody know what the other 3 are? No? Great. Because my next view graph then will tell you that. Essentially, 4 things in that speech. The first was the moon landing, which we did. The second item in that speech was he wanted to greatly increase funding for the rover nuclear rocket program. Again, this was in that same speech. And the reason he gave for that was to accelerate development of the rover nuclear rocket. This gives promise of someday providing a means for even more exciting and ambitious explorations of space, perhaps beyond the moon, perhaps to the very ends of the solar system itself. Okay, that is in the same speech. And the third and fourth items were the development of communication satellites and weather satellites. We've done 3 of those. And NASA really, well, I mean, I really want to try to see, along with other interested NASA scientists and industry engineers and scientists, see if we can't get this country back on a track to developing nuclear rocket propulsion so that we can truly do the kinds of exciting missions that everybody, I think, here in this room wants to do. Between 1955 and 1973, there were 20 rocket reactors which were designed, built, and tested by the United States out in the Nevada test site at a place called Jackass Flats, Nevada. I mean, the amount of money spent during that time period was about $1.4 billion. You take that amount of money and you escalate it up to today's dollars, that's equivalent to $10 billion of investment in technology today. Okay? This is an experimental engine, the NRX-XE engine. This is the reactor core down here. Here's a portion of the nozzle. There's a big duct that blows the exhaust gas out the bottom, turbo pumps, and there's a big hydrogen tank up there. This engine was operated over a 3-month time period. It did 23 startup and shutdowns. Each burn was over 15 minutes. And some of these same kind of engines operated producing 55,000 pounds of thrust for an hour at a clip. That means that engine just turned on, produced 55,000 pounds of thrust, and operated constantly for 62 minutes. That's pretty remarkable stuff. So nuclear propulsion, we developed the technology 20 years ago that demonstrated the specific impulse, the thrust levels, the hydrogen exhaust temperatures, and burn durations that could send us to Mars today. We have already demonstrated that technology 20 years ago. Okay? And we've just kind of let it sit there and not really do anything. So the technology is there, and again, that's a 20-year-old engine. We can do this engine better, lighter weight, higher thrust to weight, higher temperatures, and even greater performance, 100 seconds greater than a nervous system. The nervous system's operated at about 825 seconds specific impulse. The best chemical rocket engine, the SSME, operates at about 455 seconds. The engines we're designing over the last couple of years with higher temperature fuels, we can get up to 940 seconds. And we're not the only ones who are working on nuclear rockets. 3 years after the NERVA program started, the Russians initiated a nuclear rocket program. And they took their fuel element concepts and technologies and temperatures to even higher capabilities than what the United States did. In 1992 and 93, 91, 92, and 93, the NASA Lewis Research Center, in its then Nuclear Propulsion Office, funded work between Aerojet, who was the original contractor to design the NERVA engines. They teamed up with a Russian group of companies and came up with a joint US-CIS engine, again, with the capabilities that I just told you. Not over 940 seconds worth of specific impulse. So we think there's some great capabilities there. The Russians still want to develop nuclear rocket engines. And I hope someday this country will kind of get on the dime, get off the dime and start working. Where are we now? Okay, enough of the lecture. Right now, you know, NASA's sitting around and you keep reading stuff in Space News or the magazines. NASA needs a space vision. You know, what do we do? I think, I was at NASA headquarters on Thursday, and I briefed a number of people from the Office of Spaceflight, the science group, and technology development on a new possibility. Why don't we contemplate focusing our resources on sending people to the moon, not just a couple of astronauts, but developing the key technologies that we need that can lead to the commercialization and human settlement of the moon. And we're going to touch on some of these issues. But this is one of the view graphs that I showed them. We need a challenging goal. You know, NASA says, well, I don't know, you know, Dan Golden in Space News was saying a simple goal is needed to stimulate the public, you know, like during the Apollo days. And he, as an example, he threw out, well, maybe we can detect a planet around a distant star. And to me, that sounds nice. That's a science type project. I mean, where's the people? You know, where's the meat? I mean, I want to get people into space, and I want people to start getting beyond the bounds of low Earth orbit. So there have been, you know, reclamas to Golden's Space News article. And again, so what we were proposing is that over the next 25 years, a major effort challenging both NASA, ESA, NASDA, the Japanese Space Agency, and the Russian organization to really think about going back to the moon and going back this time with the technologies you really need to make this thing pan out, to get people there, to make industry viable. Industry can underwrite growth. Growth can underwrite more private citizens getting there, and that's what we think we want to try to do. See if that's feasible and see if that's viable. That's our target. You see it every night. I mean, it's not some distant speck like Mars. Mars is a hell of a long ways away. Okay? Just because you look through the telescope and you can see it, I mean, it's still far. This thing you can see with the naked eye, it's 3.5 days away. Okay? And it could be even closer. You can get there. It's reasonable communication time, not 22 minutes, 2.6 seconds. And you can carry on a reasonable discussion. Remember, a lot of people in this country say, we've already been to the moon. Well, that's pretty arrogant. You know, the United States has been to the moon. The Europeans haven't been to the moon. The Japanese haven't been to the moon. And the Russians sure as hell tried to get to the moon and beat us. But they didn't. They sent probes down, and you can bet your pants they would like to put a cosmonaut down on there. So I think that the moon could be the 21st century next frontier for this country to really embark on. All we need to do, we need public support on this. And I mean, I think the National Space Society is the type of organization with the greater number of people that need to hear that kind of voice. The moon's got an abundance of resources. 43% of all of the weight of the moon is oxygen. And a heck of a lot of chemical rocket engines use mostly oxygen as their propellant. Okay? So, and there's a lot of other things. There's metals, there's ceramics, there's a lot of solar, wind, and planet volatiles, which are sources of carbon, nitrogen, hydrogen, and so forth. The moon also offers a large, stable platform for us to do all kinds of science missions. If we really do want to do science, I mean, the moon represents an atmosphere-free platform, large stable platform. On the far side, you also have a platform that's free of electromagnetic radiation to really probe for these distant stars or planetary type systems. And I think most importantly, although we keep talking about space station freedom as being, you know, our first foothold, you know, off of the planet, I mean, it's like still being in the backwater gulches of a river. I mean, you're in this little pool that's just kind of spinning around here. You got to get into the mainstream, out into cislunar space and out into interplanetary space. I think the moon is really the first major extension of man into another planet. I think we can do it. Well, we know we can do it. We've done it before, but we think we can do it, allowing a lot of people to get there. Key ingredient in space transportation. We all know about Earth to orbit. We definitely need low-cost access to space. Key ingredient is what kind of low-cost access to space. I think maybe you might need two kinds. You need something to get people into space. Could be a single-stage to orbit vehicle, right? Good for space tourism, good for all this other good stuff. And then you also need something that can carry something. I mean, it's got to have some payload volume to it, all right? So we may need something like a heavy lift launch vehicle. And you may need to be able to launch the basic components of the spacecraft. Because if you don't, then you may have to do a heck of a lot of on-orbit assembly. So it could turn out to be economically, you know, less attractive. There were a lot of space vehicle designs that were looked at from 1987 all the way to 93 when SCI kind of went away. I mean, there were two-stage vehicles with aero brakes, totally integrated vehicles with aero brakes, and all these strap-on propellant tanks that were jettisoned. I mean, very complex vehicles. I mean, that's the front door right over there that the astronauts were supposed to crawl in, and with the drop tanks not shown. I mean, after I guess the guys got in, then they bolted these tanks on there, and wow, yeah, it's pretty rough. You know, especially putting all that stuff up in space. Then that was looked at during the 90-day study. Then many of you are probably familiar with the synthesis report, the study done after the 90-day study. They wanted to go to larger launch vehicles rather than shuttle-derived vehicles. Go to something like a 150-ton heavy lift launch vehicle. 2 launches of that. You rendezvous and dock this piece with that piece, and you got a spacecraft in orbit ready to go. But again, those vehicles bigger, way more, and a bigger heavy lift launch vehicle, so a lot more cost. You know, maybe there's a lot of concepts that are being talked about for low-cost access to space. We need them in all kinds of payload capacities and growth capabilities. But I mean, during the 90-day study, there was a concept that was thrown out. It was kind of like the Shuttle C. I mean, with the basic shuttle technology and getting rid of the orbiter and putting on a dumb cargo container, you can put up between 60 and 70 tons of mass in low Earth orbit. If you rack up the launch cost for that versus even what the RLV is, the launch costs are pretty comparable. Access to space study said something like an RLV, single stage to orbit, $41 million a flight, putting up 25,000 pounds, comes out to $1,640 per pound. Well, this concept can put up 155,000 pounds of thrust, of payload, and for $200 million bucks a launch. That comes out to $1,680 a pound. So, I mean, we may need vehicles in 2 sizes, so keep that in mind when you keep hearing people say single stage to orbit, single stage to orbit. I mean, we need a couple of different concepts here to make these things happen. Aside from those vehicles, they were all expendable. During the same time period, we looked at nuclear thermal rocket vehicles for missions to the moon. For the same amount of mass, or even slightly less, a nuclear thermal rocket stage could take out a lunar landing vehicle and its payload, all propulsively capture into orbit, whereas the other missions left the lunar landing vehicle behind. The nuclear thermal rocket stage can bring it back to Earth and propulsively capture into low Earth orbit. Not need this big aero brake, you know, to scream on in. It could bring everything back, jettisoning nothing. So it's fully reusable for less mass, less cost, using a technology that was, again, developed 20 years ago. And that's just an artist's illustration of what that vehicle might look like. The problem with this concept, however, although it's got great high specific impulse and thrust, it uses only low-density liquid hydrogen. So the volume of the tanks are large. The diameter of this tank is 10 meters. 10 meters is what you see when you go to KSC and the other place and you see the large vehicles laying on their belly out, the Saturn V's. The lower stages are 10 meters in diameter, so that's big. We want to get down smaller. The other key ingredient, the moon's got, the other thing is that the moon has a lot of resources. This is a picture of a lunar oxygen production plant based on the hydrogen reduction of ilmenite. Ilmenite's a mineral, one of many minerals on there that contains oxygen. By reacting it in hydrogen in a fluidized bed, you can generate hydrogen, which you then recycle back to mix with more ilmenite, and water vapor. Water vapor it produces. And the water vapor you electrolyze, you take the hydrogen, recycle that back. The oxygen you take, you cool, you liquefy, and you use it for rocket propellant or air breathing or for fuel cells or for your lunar base. Okay? So there's been 12 different technologies identified for producing lunar oxygen, and they've been demonstrated already on the ground, so we know we can do this kind of stuff. Chemical rockets have the advantage over nuclear in that ultimately, you know, they could go to the moon, produce lunar oxygen, and have return propellant, whereas a nuclear thermal rocket would maybe use only hydrogen all the way out and back. So that's going to kind of hurt us. So we were really thinking, how can we capitalize on the high performance potential of a nuclear thermal rocket and be able to leverage oxygen? They don't seem to be compatible. I don't want to inject oxygen into a reactor core because if you just eat it, it'll erode it. Okay, with high temperature oxygen in there. So so the key ingredient, how do you marry these two? The answer is we come up with a concept which we call the LOX augmented nuclear thermal rocket. It is essentially a liquid hydrogen cooled nuclear thermal rocket. Let me just go right to the view graph. Conventional liquid hydrogen cooled nuclear thermal rocket engine, subsonic after the hydrogen's heated. It goes sonic in the throat, right, Mach 1. Then it starts expanding into the nozzle, going supersonic. We would inject oxygen into the supersonic hydrogen and get additional supersonic combustion as well as thrust augmentation. Okay? It's essentially scramjet propulsion in reverse. Single stage to orbit air breathing systems that are being talked about would use the ramjet, scramjet rocket in the orbit. Okay? In those kind of systems, we inject hydrogen into supersonic air and oxygen. Well, in this concept, we're doing exactly the opposite. We're injecting oxygen into supersonic hydrogen. Okay? Well, why do I want to do that? Well, in a simple system operating at constant power, this engine can give you variable thrust and ISP capability, while the reactor is operating at constant power. By just putting your foot down on the oxygen accelerator pedal, if you will, that turbo pump can start increasing the oxygen to hydrogen fuel mixture ratio. Chemical engines operate down around 6 or 7. By increasing from 0, which is all hydrogen, to 7, the ISP drops because we are putting more hydrogen, more oxygen in, higher molecular weight. So we drop from 940 seconds of ISP down to about 515. That's still 65 seconds, even at oxygen to hydrogen mixture ratio of 7, that's still 65 seconds better than the best chemical rocket we have right now. And the key thing to keep in mind is that now when we go to the moon, we can produce oxygen to refuel this baby for the way back. So those ISPs are effectively doubled, maybe even tripled in terms of what they are. And not only does it have that variable thrust and ISP capability, as you see, for a simple 15,000 pound thrust engine, all hydrogen, it would have a thrust to weight of approximately 3. By increasing that oxygen to hydrogen mixture ratio, that increases to 13.1. Two 15,000 pound thrust engines generating 30,000 pounds with liquid hydrogen alone. If you increase the oxygen to hydrogen fuel mixture ratio to 3, you'd be generating 82,500 pounds of thrust. So big engine performance out of little engines. Okay? Other key ingredient is the tanks get smaller. Because now you're replacing part of the low density hydrogen volume, big size, right, with higher density, smaller size liquid oxygen systems. That's kind of summarized over here. What we call the lander or the LOX augmented NTR, this is not your father's NTR. Okay? This is a new system with great capability. It leads to smaller, cheaper engines that give you big engine performance. Because you have small engines, now you can put them, if we test today, we can't test out in the open like we did in the Nerva days. We have to have closed, we have to have contained facilities, trap all the exhaust, clean it, purge it, contain it, and just exhaust clean hydrogen stack gases and burn those. Okay? This makes for a lot smaller facilities and cheaper facilities. As I said, we have variable thrust and ISP capability. By the engine being able to increase its thrust for departing, say, Earth orbit, the burn durations of the engine are now shortened. Gravity losses go down. The effective life of the engine goes up. Okay, we can run it longer, do more missions per given engine life. The reduced propellant tank size leads to smaller mass, smaller boil-off. We also have reduced vehicle sizes, smaller stages, smaller launch vehicles. Vehicles that we originally needed 10-meter diameters for, now we can put on these Shuttle C class vehicles. Something that we can develop potentially economically without having to develop a gigantic launch vehicle system. Just to kind of gives you an idea, the Nerva program, 75,000 pound thrust engine, but with a Russian fuel element type in it, would have about 940 seconds. You can see it's big, 75,000 pounds of thrust. You don't have any engine out capability. You lose one for some reason or another, you're kind of stuck. You can put dual turbo pumps on there for reliability, but it doesn't give you engine out capability. These two small engines now, two 15K engines, oxygen to hydrogen mixture ratio 3, are producing more thrust than that. You lose one, you still got a single engine providing you return capability, increased reliability. So there's a lot of fantastic performance we believe in here. And as I mentioned, smaller test facilities. This kind of gives you an idea. Here's a man over here. That's an 80,000 pound thrust engine, approximately Nerva size, 40,000 pounds, 10, 15,000 pounds. $1 billion test facility, $110 million test facility. Order of magnitude type reductions. We can test these things maybe out at Idaho National Engineering Lab, potentially out at the Nevada test site with small containment building. That's the concept. What can we do now with regards to missions? How can we go back to the moon and do the kinds of stuff that I was talking about in the beginning? Put down lunar bases, start producing lunar oxygen, be able to start the beginning of some kind of industry infrastructure, allow people to start going there who are more than just a few select astronauts and techno scientists. We can start putting greater numbers of people. How do we do that? The strategy that we've talked about is following along these lines. We want to try to make sure that this thing can be done in an economical way. We won't have an SEI. That's not to be. We definitely have to get industry involved. We don't want to draw a lot of attention to ourselves. We want to identify the key technologies, start developing, put the framework in place so that if support develops, we've got the technologies available. But the key thing is we want to reduce upfront investment costs in the beginning. We can't go out here saying, well, I need a big, gigantic space station with a space hangar. I need all kinds of propellant fueling depots and all that kind of stuff. We're not going to be able to afford that to begin with. We've got to get rid of these gigantic launch vehicles. We went from 120 ton in low Earth orbit to vehicles which are as big as 240 tons during the first lunar outpost activities. We want to get those costs dramatically down. Plus, we want to maximize the amount of payload we drop on the lunar surface for each mission, because that translates into major dollars. You've got to remember, for a chemical rocket engine, it takes 7 kilograms of mass in low Earth orbit you have to launch for every kilogram you want to put down on the surface. Okay, so whatever the dollars per kilogram are to low Earth orbit, multiply that by 7. That's the cost to put that kilogram on the surface of the moon. Got to get the cost down, all right? That's what we're trying to do. But then ultimately, you can't throw away everything too, because that's going to eat your lunch. You got to ultimately minimize recurring costs, and that means you got to kind of move to reusability. How do you do all that stuff? Well, we've been examining essentially an evolutionary approach. What we would do is, again, the benefits of the LOX augmented engine. I mean, it's got all this great capability. Where its power really is when you have a refueling source. I mean, if you're volume limited, you could use it from the scratch to shrink the size of the vehicle and put it on a launch vehicle of some given capability, but you don't have the high ISP. Okay? So initially what we would do would be utilize small engines, two 15,000 pound thrust engines, all liquid hydrogen, to send out, and we'd operate them in an expendable mode in the beginning. That reduces the size of the vehicle, increases the amount of payload we can drop down on every single mission, because we don't have to take down all this payload to capture back in the Earth orbit. And that's going to allow us also to use smaller engines, because the total mass in low Earth orbit that we're putting up is lower. Okay? Next, by shrinking down the size, that allows this expendable NTR approach to be put together using two simple Shuttle C launches. Rendezvous and dock in orbit, we're ready to go to do a lunar cargo mission or a piloted mission. We don't need, again, with technology that we can develop for maybe $3 billion, something like the Shuttle C, with 60 to 70 tons capability in orbit. Cargo missions would go out first. The key ingredient is to try to produce lunar oxygen as soon as you can, so that initially You can use them to refuel lunar landing vehicles. As soon as you can start refueling lunar lander vehicles, that makes a major cut in the amount of payload you have to launch. Okay? Even if you save 5 tons of propellant to come up from the surface, translate that back, 5 times 7, that's 35 additional tons you had to launch into low Earth orbit at whatever the launch costs are. So there's potentially a viable commercial market right off the beginning in lunar oxygen production. So we refuel lunar landing vehicles initially, and so that they become reusable. Now our transfer vehicles, all they do is go back and forth taking out payload. They don't take out landing vehicles and propellant. They take out 100 tons of payload every mission. Okay? And then once that lunar landing vehicles are now reusable, they can start taking up propellant for the lunar transfer vehicles. And it is at this point that we transition from our expendable mode to our reusable mode. Our small 15,000 pound thrust nuclear thermal rockets, they're the same engine. We just unscrew the old hydrogen nozzle and put on the LOX afterburner nozzle with some appropriate modifications, of course, and a LOX tank up in the front. But then that same engine then can now start doing reusable missions, and we would transition from our expendable to reusable, and the accumulated cost, that helps to reduce our recurring cost, and the profit that is made, that can eventually then be fed in gradually, if you will. If industry is in charge and looking to make money, they're gonna say, I want to keep this thing going. I need a refueling depot here, I need a refueling depot there. They'll reinvest their bucks in there to set up the infrastructure, okay? Here's a quick picture of what these vehicles look like. Kind of lined up. Here is a chemical system. It's launched on 2 shuttle-derived vehicles, 66 tons in low Earth orbit apiece. Rendezvous and dock, that's 132 tons. First launch puts in an expendable injection stage. The second stage puts in the second portion, which is the lunar capture and Earth return stage. The lunar landing vehicle with anywhere from 0 to 5 tons of payload, depending on whether this lower stage here is used to assist, does a suborbital burn, much as we did during the Apollo program, where the 3rd stage helped to boost the Apollo Command and Service Module and LEM into low Earth orbit. You can get a little bit of additional performance. If you can do that, maybe you can get up to 5 tons. Without it, I mean, you can't. I mean, you may be putting in 1 or 2 tons, comparable to the Apollo program. And then all you do is come back with a capsule. By contrast, for the same 132 tons, launched on the same 2 shuttle-derived vehicles, this pilot vehicle with 2 15K nuclear thermal rockets can put 9 tons. Okay? In a cargo-only mode, where we get rid of this capsule and the capsule here and just put on cargo, that stage can take out close to 40 tons of payload on a single one-way trip. So these vehicles can put down significant infrastructure, small, it's already established base, ready to just occupy, a modular lunar oxygen plant, modular, ready to land and start sucking in hydrogen, being fed lunar regolith and producing oxygen. We can do that with these modular units. And once oxygen is available, we transition, as I said, to this reusable phase. This was an expendable vehicle. This is a reusable vehicle. Now with the LOX afterburners. It is smaller, it is fully reusable, it burns both back and Earth for capture, and it carries out over 400% more payload than you did with that expendable vehicle. And it needs 21 tons of lunar oxygen in this small little LOX tank here. Okay, it's all Earth-supplied hydrogen, but again, this vehicle now can provide the basis for the setup of an infrastructure which can send us back to the moon, and a reusable one that can be developed economically, using lunar resources, can be launched on shuttle-derived technology and not a monstrous heavy-lift launch vehicle. And what's, I think, more astounding is that this same vehicle, if you get rid of the capsule and put a 25-ton passenger module on there, they can carry 20 people to the moon. That same vehicle can do a 36-hour one-way trip to the moon. And if we would then refuel with about 48 tons of lunar oxygen and come back in 36 hours. This larger vehicle here does 24-hour one-way trips to the moon. You'll notice the mass there was about 250 tons. If you recall those earlier vehicles I showed you during the synthesis group in the SEI days, they were 280 tons, and they weren't doing anything like this. 24-hour one-way trips to the moon and back. in the remaining time I have, I'd kind of like to take you on what an imaginary trip might be like to the moon. You're a commuter, the lunar oxygen plant is set up, and by golly, you're the supervisor, something's gone wrong, and you got to get out there. And you got to get out there kind of quick. You only have a week, all right? So you can't afford 3.5 days out like the Apollo program, 3.5 days back, because you're not going to have very much time there on the moon. All right, so we're going to talk about commuter flights. Okay? As I mentioned to you before, it takes a heck of a lot of energy, and I'm not too sure people realize that. The combination of injection velocity delta V to depart low Earth orbit and capture delta V to capture in the lunar orbit was about 4.1 kilometers a second for the 3.5 day out, 3.5 day back Apollo style mission. As you start going to shorter and shorter one-way trip times, the total of those two components increases dramatically. And at 24 hours, you're up to 6.9 kilometers a second. I mean, get close to doubling this stuff. I mean, that's more than what we need to go for low energy missions to Mars. So this thing is really moving. There are no free returns. There are no swinging around and coming right on back. You are on the way out. You definitely need multiple engines. In case one craps out, you do have a second which can stop you because you're just heading on out into heliocentric space. So we are really traveling. We're at escape. Okay? But you can see the dramatic increase. You're putting a heck of a lot of energy into this vehicle. To get there quickly, you got to take that out in order to stop and be captured. Just this kind of gives you an idea. This 36-hour lunar mission, this LOX-augmented NTR, 25-ton habitat out and back. This shows the mass and low Earth orbit that would be required as a function of the outbound oxygen to hydrogen mixture ratio for varying inbound mixture ratios. It's just a parametric. You see the characteristic, minimum, the optimum, the minimum saddle point. And you can see here, this is, if I take 0 and 0, all liquid hydrogen nuclear thermal rocket, which is pretty darn good, by the way. I mean, it's 375 tons to do 24-hour out, 24-hour there, 24-hour back, all Earth-supplied hydrogen. I mean, that's big, okay? So by going now to the LOX-augmented mode, operating at an outbound to inbound mixture, ratio and an inbound mixture ratio of about 3, we can do that mission I just showed you. With this small vehicle, right here. Again, another key ingredient. This vehicle right here, this whole vehicle in its entirety, but not fully fueled, but the entire vehicle can be launched on one launch, on one of those Shuttle C launches. Now going to 24 hours. I mean, it's even more dramatic, as you see, because the delta V's are so much higher. Our optimas are somewhere down here around 250 tons. And again, if you try to do it all liquid hydrogen, I would say it's impossible at 1,000 tons. So, I mean, this is literally, what we're talking about here is literally the kinds of space transportation that was portrayed in the movie 2001: A Space Odyssey. We can do it, I think, with technologies that we can have in the next 10 to 15 years. All right, how does our typical flight go? All right, let me stop talking here and show some pictures. Well, I think it might start by us going to a conventional type of airport. But now we've got space planes also operating. Planes that you can board. I don't know whether they're wingless and and vertical launch, vertical landing, whatever the single stage to orbit concept is that wins out, is technologically the best. Hopefully there'll be a version of that developed to allow people to get into space. And not just some small, tiny amount of payload in a vehicle that all we're doing is just using it as a logistics ferry, to put up a little bit of payload to the space station. I mean, we need to have a bigger vision than that. But that would be the first step. That gets us up to our International Space Station or spaceport, where you would rendezvous and dock. And then there, you would get on the space bus or space hab module. You'd board up, it would undock, it has its own little bit of reaction control system propulsion, its own guidance, navigation, and control, minimum life support, but adequate, but it's not something that's going to, you don't have a system that's going to last 500 days. It's sized for the mission, then undocks from the space station, and then docks with the lunar transfer vehicles. Either your 36-hour vehicle or your 24-hour vehicle. And then after that short duration, at 1 to 1.5 day trip to the moon, the lunar bus here undocks, the lunar HAB module undocks, and is essentially moves up, rendezvous, and docks with a lunar surface-based landing vehicle. It's based at the moon, gets lunar oxygen from the moon. It's kind of like a Sikorsky helicopter. Underbelly, grab, and landing. Takes it down to the lunar surface, shown here, where a little surface transport car is awaiting it. It's lowered, is grappled, and then it takes it on over to the space station, or I'm sorry, the lunar base, where you'd have your meeting, and the vehicle would dock with the airlock. Potentially be doing this in kind of a shirt-sleeve environment, without a big major spacesuit, you know, and like the astronauts going for the shuttle launches with helmets and life support cases and hoses hanging all out of you. It can be something that can actually get significant numbers of people into space. I'd like to mention one other thing in this scenario here. You know, a 24-hour trip to the moon. Right now, if you get on an airplane in Washington, D.C. and fly to Sydney, Australia, what a lot of people like to go to Australia for Melbourne and all that kind for vacation, it takes 24 hours. So in the time it takes you to go from Washington, D.C. to Sydney, Australia, you can travel to the moon with this kind of technology. Okay? I mean, it does take investment in technology. It does take a NASA with some vision. It does take, I think it also takes a country that is receptive to ideas like this. I mean, right now, if you pick up the front page of the paper, it says, you know, Lewis may be saved from shutdown. You know, I mean, some people say, Stan, I'm not worried about going to the moon. I'm worried about whether I'm going to have my job next week. I mean, the whole government is going through a reorganization here. Major downsizing. We really have to think about these endeavors in an international forum with international collaboration. And I really do think the government is no longer going to be the big feeding trough for everybody. Industry is going to have to kind of step on in if we're going to do some of these things and see that there's some kind of commercial market. See that there's an opportunity there to send people into space, get people involved. Because dollars will ultimately be the key ticket item. Let me give you my last few graphs to summarize, and I'll take whatever questions you may have. I'm running, I guess, a little bit fast, but I think it's supposed to be about 45 minutes or so. I think a return to the moon initiative focusing on commercialization and human settlement of the moon is really something that should be given serious consideration. When you go to headquarters, and when I was there on Thursday, I started briefing these guys on this kind of information, but in a lot more detail with dollar amounts and stuff. And I told them when we first started, don't think about this mission from an exploration and a science perspective. I said, I ain't interested in exploration. I ain't interested in science. We'll sell that to the highest bidder. Sounds a little bit mercenary, but I think that's what it's going to take to get people into space. I mean, the great activities in the Middle Ages, you know, the spice trade, I want silk, I want spices, I want gold, and all of this good stuff. I mean, that's what drove early exploration. It was the prospect of making money. And for a lot of you here, you probably have heard about heard of Tom Rogers, who's always talking about space tourism. I mean, I think there's something definitely credible there. You know, if you get large numbers of people in space, you know, space tourism could actually make the reusable launch vehicle something that industry can actually bite off and try to develop, because you'll almost immediately double your market, right? So it's a key ingredient. So I think you want an initiative that's going to stimulate industry, get the public involved, and I don't mean just a couple of astronauts. I'm talking about the people. NASA's job, the other space agency's job, is to open the space frontier to mankind. I think, you know, we think we're doing that by, you know, the shuttle going around and around and around and around, and we're doing stuff. But I mean, we're not really doing it. I mean, you know, you don't have a bunch of wagons on the line and somebody's not going, go! And, you know, everybody's running on out there staking their claim. I mean, NASA should kind of be about that. Maybe not now, but I think they should definitely be in their plans. Japan and ESA are definitely interested in the moon. you don't hear very much about them saying, I want to go to Mars. Okay? The Russians say, oh, let's go to Mars with the United States because, well, you know, we got beat. The Russians got beat going to the moon, so they really weren't interested in going to the moon. But the moon, I think, is near term and it's credible. The Europeans and the Japanese want to go there. I think the Russians would definitely like to go. The United States finally has gotten off the mark, I think, and NASA essentially has picked the Lunar Prospector for launch in '97 as part of its Discovery mission. It's a mission which will go to the moon and do a detailed map of the lunar surface. So that's, I think, very valuable. The moon is definitely nearby. I mean, it's incredible to think about actually going there, settling there, and developing commerce. If you can't do it on the moon, we ain't never going to do it on Mars. I mean, it's insane to think that you're going to do that. I don't care who your greatest spokesman is or advocate for it. You've got a long ways to go before you're ever commercializing and settling Mars. It's just a hell of a long ways off. We don't have the technology to get you there in quick time. The LOX-O-Manted nuclear thermal rocket combines two simple technologies. Nuclear thermal rocket, which we've already demonstrated, and scramjet propulsion, which there's a lot of money being dumped in all across the world in terms of hypersonic research. I think the marriage of those two technologies can be accomplished in the next 10 to 15 years, and I think it can really lead to a revolutionary space transportation system for the moon. Another thing to keep in the back of your mind, I've only talked about the moon, but you know, what's out there as you go from the moon to Mars, to the asteroids, to Jupiter? There's a lot of water, okay? They think there's a lot, well, we see there's water on the North Pole of Mars, right? Maybe a lot of water on subsurface permafrost. A lot of the asteroids, carbonaceous chondrites, could be up to 30% water. Beyond the asteroids, there's Jupiter with its moons, Europa, Ganymede, Callisto, all water ice. They think there may be big oceans of water under Ganymede and Callisto and Europa. Okay? So you can see this kind of propulsion allowing you to go from point A to point B, point C, point D, and then back. You don't need gigantic fusion, space arc drives, or any super advanced concepts. You can do it with technologies that we can develop in the near term. All components can be launched on small launch vehicles. Again, we need to be frugal in order to get these things going. We're not going to have big vehicles. And then finally, I think this kind of technology can lead to some pretty spectacular missions even to the moon. Making things like 2001: A Space Odyssey fact and not fiction. Thank you very much, and I'll be glad to take any questions. First hand back there with the red.
I've got a couple of questions here. One of them is, who do you envision doing this? Do you envision NASA doing this? Or do you envision, like, say, some large international public-private consortium as another example that would be something that would be able to provide a decouple the effort from the year-to-year political funding cycle, et cetera?
Exactly. It's a big question. Yes, I think to all the pieces with regards to, I think to get started, one of the things we proposed, was final bullet on a few graph we presented, we suggested that NASA, within the next 6 months, sponsor a big workshop on that title, commercialization, human settlement. You bring in government researchers, you bring in industry researchers, you bring in academia, and you bring in the public. Key ingredient. I mean, they've got to see that the public's really jumping around and is interested in this stuff. I think just the way the RLV program is being talked about, government coming in, spending, I don't know, maybe $1 billion to develop key technology and do, the X-33 program, experimental subscale flight of a vehicle or scale of a vehicle, and then if it's shown to be economically feasible, then the industry goes out and develop it, but the government contracts with industry to procure services. So you can see them signing some arrangements. It costs us a fortune now. So if the launch costs are reduced by an order of magnitude, come in and pay them twice that amount. So the industry's making a profit, government's certainly saving, and industry's starting to get involved in the hopper. I'd see this being done for a lot of the important technologies that you need to make all of those things done. Yes.
Then the second question I had was regarding reactor safety. Yes. And kind of the current, the political, social considerations of all things nuclear.
Yes.
And how would you deal with that? Because basically you're going to have these reactor cores that you're going to put into space, and
Yes.
they're going to be there permanently.
That's right.
Someday you got to get rid of them.
That's exactly. I don't have time to go through all of it now. I've got reams of papers that I can send you, but in all of the scenarios that we talked about here, disposal is already figured in. I mean, these things, again, depending on what temperature you want to run them in, run them at the reactor core, how hot the core is operating and the hydrogen is that is flowing through it. They can run anywhere from 5 hours to all the way up to 30 hours.
Well, short
Okay?
version, where do they go?
Yeah, you can send them on heliocentric disposal. I mean, we got this lunar vehicle going back and forth. On its last mission, it's getting near the end of life. You stick a payload on it, and you inject, you launch it to the moon, okay? The payload separates, it goes, does its landing, and you just do a small retargeting mission, and that lunar stage does a lunar swing by and is sent out into heliocentric space. We've done detailed encounter plots, and it's 100,000 years up to 1,000,000 years before there's any chance of re-encounter. By the time that thing came back, you could cut it up with your thing and use it as a lead paperweight. Next question.
Well, all this is fine, but how do you get the Luddites to give you permission to launch it in the first place?
I think industry is going to dictate that. Money is going to dictate that. And I think the general public, if you can show, the people who are developing it, right now, if you look at launching nuclear systems, I mean, there have been a lot of protests right on all the missions. They've all gone, though, haven't they? That's because the government, although you hear all the publicity, there's credible engineers, credible researchers, credible industrial people putting together all the numbers. They go before the dictated set of INSPRI review panels, and the ultimate example is that the risk is always shown to be significantly less than the benefit, and NASA and industry have done a very thorough job in showing that those risks are reduced, and they always pass. And I think you're going to see that more and more and more as time goes on. This question right there, and I'll get you.
Okay. Is this a thermal reactor or a fast reactor? What type of moderator does it use? Graphite, maybe? What's the control rod material? Boron or hafnium? How do you prevent fuel element degradation? What's the cladding made of? Zirconium? What's maximum core life and full power? What's core nameplate power? What type of fuel cycle do you use? Uranium-233, thorium-232 slow breeder, or just straight 235?
Enriched-235 is uranium, zirconium, niobium carbide. It's a ternary carbide.
Do you use a carbide fuel then?
Yeah. Well, in this particular, there are we've looked at 4 different reactor concepts. One is a uranium oxide tungsten Cermet fast reactor. The other 3 were all thermal reactors, carbide class fuels. Some were in particles. The others, the NERVA program was hexagonal fuel elements. The Russian fuel element that I talked about right now, there is axial, but the length, it's not an entire fuel element. They're chopped up into 100-millimeter long fuel bundles of little swizzle sticks to maximize surface heat transfer and maximize power density. Each one is graded and contoured in terms of enrichment as you run down the length.
What is the enrichment?
In most nuclear thermal rockets, it's 93%.
Same as the Navy submarine core.
I'm not a Navy guy, so.
Is it neutron? What's the neutron exposure to the crew, and what's the gamma exposure to the crew, and what type of shielding do you use?
Again, a whole range. I mean, from tungsten. I mean, you need obviously high Z and low Z materials for a nuclear thermal rocket engine because you've got both neutrons and gamma rays. Right.
Lead is good for gamma.
Right.
Hydrogen is good for neutrons.
And the NERVA program. I mean, that's really the final composition will actually be the result of detailed calculation based on vehicle design. Well, no, we do now. I mean, we've done Mars vehicles, we've done lunar vehicles. And for that, the lunar vehicles that we've showed, each one of those engines has a disc shield in front of it, okay? And inside the engine, there's a dome shield inside the pressure vessel, okay? It protects the turbo pump. So we're protecting the equipment as well as having a disc shield to protect the crew. Plus, you got this big long tank of liquid hydrogen up there, which also protects you during a major portion of this mission.
Except at the end when your fuel tank is empty.
That's right. Well, that's why you have to design your shielding systems for that final period.
And do you use control rods?
Yes, we did. We definitely did. We got
hafnium?
Your NERVA program, they could be any one of a number of combinations.
boron
Boron
carbide.
carbide, boron carbide, yeah, any of the high neutron absorption cross-section materials can be used. From Friday, got the good, right thermal characteristics, cycling and so forth. But B4C is one that has been looked at a lot.
And you use controlled startups, and you
Definitely.
never have reactivity in seed beta bar. The delayed neutron speakers are
During the NERVA programs,
there was a graphite pulse one that did go prompt critical, but it's a bad idea.
That's right, there were, but they definitely have demonstrated controlled startups. I showed you that engine, the XE.
Right.
That one did 23 startup shutdowns.
And is there fuel element degradation?
Yes, there definitely is fuel element degradation. Again, you can coat fuel elements with zirconium carbide, niobium carbide,
But
to
at
prevent
2,000
hydrogen attack. But that's why I showed you that chart.
Right.
You know, if you run at 2,900 degree Kelvin, you may have 5 hours of life.
Yeah.
Now, that sounds short, but each mission is a half an hour out and back. So that's 10 missions. A 30-hour one would be 60 missions. I can run this engine weekly for a year before I have to replace it. Let me just get a couple.
Well, what I'd like to do is to ask, will you be available for questions out in the hall? Or?
Yeah, I will.
Okay. We are down to our 5 minutes, and we're running a pretty tight ship here. So what I'd like to do is to break at this time, and Dr. Borowski will be available for questions out in the hallway. And we will need a few minutes to get ready for the next talk.